In the projectile motion, we're going to take the simplest case when we shoot a projectile horizontally, and then it will fall off downward as it's shown in this diagram. This is a typical two-dimensional problem. As we said, our strategy before for two-dimensional motion, we're going to choose the coordinate system as a Cartesian coordinate, where the horizontal axis is going to be the x-axis, and the vertical axis is the y-axis, and the direction positive upward. The initial conditions of the problem, we're going to set the initial position for x and y as 0 at time t equals 0. This will simplify the problem. And however, we have, as usual in two-dimensional motion, in our case here, the projectile, we have a horizontal motion and a vertical motion. In the horizontal motion, the velocity is constant. The initial value is the same as the final value. And in this case, the component of acceleration along the x-axis is 0. This is because we don't have any force acting along the x-axis. The only force is acting on the ball when it's falling is just the force of gravity. That's why along the y-axis, in the vertical motion, we have the component of acceleration ay. It is the same as the acceleration due to gravity, and the minus sign indicates that the pulling on the object is downward. That's why the acceleration is downward. In this simple case, when you shoot the ball horizontally, it means the angle is theta naught. The initial angle is going to be 0. That's why v naught y, the y component initially of the initial velocity, is going to be 0, because sine theta naught is 0, and v naught y is nothing more than v naught sine theta naught. Our equations we used in two-dimensional, which are vx equal v naught x plus ax along the x-axis, and along the y-axis is vy equal v naught y plus ayt, and the other equation is for delta x for the displacement along the x-axis, and that for along the y-axis. And this is also the other equation of along the x-axis, the y component. If you can notice here, we can just put this 0, because this 0, because as we said, there is no motion along, there is no acceleration along the x-axis, there is no force acting it. So we're going to get vx is the same as v naught x. This means that the velocity is constant for the whole trip. Similarly, in this equation, we're going to put here ax equals 0, because again, this is the same as above. And also for this one, we're going to put this equal 0. In this case, out of the 4 equations, or here 3 equations, we're going to have just 2 equations. The first one is the x component of the velocity initial is the same as the final, which means that the velocity component here is constant. The second one is just delta x equal the product of the component of velocity y time. And this component of velocity could be the initial one or the final one, because they are the same. So it doesn't matter if you write v naught x or vx. But if you have the information about v naught and theta naught, then you have v naught x, and then you can put your own values in here. It depends on what is given in the problem. So, however, along the y-axis, the vertical motion, as you can see, we're going to replace ay by minus g, as we indicated before. In all these equations, we're going to replace ay by minus g. And in this case, you're going to get these equations are well set it up for use in the projectile's motion, whatever the case of the projectile motion is, if it is shooted initially horizontally or below the horizontal or above the horizontal. These are the equations for the projectile motion we're going to use in this session. In the as we know that the x and y motion are two independent motion, we're going to work on the x motion as if the other motion is not there, but the use of the equations as a summary is going to be in this way. And we have to remember one thing, that there is something common between the x motion and the y motion, that is t. T is the same for the x motion and the y motion. Okay, so we have to be very careful when you use this equation. We have to use the proper signs for delta x and for x for vy as well, and delta y. For delta x, if we're going to consider most of the time delta x as positive, as long as it goes towards the positive x-axis. However, for the y motion, if the projectile or the ball is going down, so we expect a minus sign for the initial velocity if it is there, or if it is zero, so we're going to get it zero. And we expect an answer for the component of final velocity as zero because it's downward, and also for the displacement y minus y naught, we expect to get a minus sign as long as the projectile is going downward all the way. This shows two diagrams shows two different trajectories or paths for a projectile. Here the projectile is thrown, let's say, from a building above the horizontal. So the projectile goes up and then down below the horizontal. This is different from the previous one, while in this case, this gentleman, he shoots the basketball with a certain height, and it goes just before, above the level of his shooting. So all these projectiles will have one common thing. We need to choose the Cartesian coordinates as our system. And again, we have to set ax as 0 because, as we said before, there is no force along the x-axis. The only force is along the y-axis. That's why we put a sub y equal minus g, because the pull of the gravity is downward on the object. Again, the initial conditions, we put the initial position for x and y, the two components, as 0 at time t equals 0. V naught, the initial velocity, as you can see from here, it has at the start of the motion two components, one along the x-axis equal, which is V naught cosine theta, and this one adjacent to the angle is going to be V naught multiplied by cosine theta, while the other one, which is opposite to the angle, this one or this one, V naught y, is V naught sine theta. So so you have to find, if theta is given and V naught is given at the beginning, you have to find V naught x and V naught y at the start. As we said before, V naught x is going to be constant all the way. V naught x is the same as Vx in here. See, the length of this vector is the same as this one. This is an indication that there is no change in the velocity along the x-axis. The only change, as you can see in the diagram, is in the velocity component along the y-axis. We started with V naught y. It seems that the arrow is large enough. Then this arrow is started to reduce as the ball or the projectile is going upward, and then the length of the component of the y velocity is changing until it reaches the top of its trajectory where Vy is 0, and then we are left just with the horizontal velocity, which is the constant one at this top. And then again, Vy started to decrease downward, and because of the symmetry, the magnitude of velocity here at this level is almost the same as the magnitude when it is downward, but with different sign, with a minus sign. And again, the component of the acceleration v naught y is equal to Vy as long as this trajectory is symmetry until this point. So if it starts from here and end up here, we're going to get at each point a symmetric point on the other side, which has the same magnitude for the y component but opposite sign. The equations again for the horizontal and vertical motion, we have just two equations for the horizontal motion, and we have the whole four equations. Actually, we just posted here two of them in this slide. We have four equations.
In this demonstration, a small car will roll down a track at constant speed. When the car reaches this point, it will fire a ball straight up as it continues to move. After the ball is fired, will it come down ahead of, on top of, or behind the car? It comes down onto the car. This shot in stop motion shows that the ball stays directly above the car at all times. What will the shape of the ball's path be through the air? The ball flies in a parabola. The combination of constant horizontal velocity and constant vertical acceleration produces a parabolic path.
The special case here in this trajectory of the projectile motion is considered as symmetrical. As the projectile is started from the origin, it ends up on the other side at the same level of x. However, when the projectile is going up in its trajectory, so the velocity vector is positive, and on the other side, on the other half of the trajectory, the component of velocity vector is going downwards. However, the value of velocity of the magnitude of the component of the velocity vector on this side is almost the same as the corresponding side along. If you take the x-axis here, a line parallel to the x-axis. While the x component, as you can see, it's constant all the time, all the way up to the end. Here, theta, the angle of the velocity, which is tangent to the projectile all the time, is positive with respect to the x motion. While the other half, on the right-hand side of the projectile, from here to here, we have the angle of the magnitude of the velocity v is making an angle below the horizontal, where in the first half it is above the horizontal. To solve such problem, as we did before, we set the initial conditions by inserting x naught equals y naught, and that equals 0. It means the initial component of the position for x and y is 0, while v naught x is equal to v naught multiplied by cosine theta naught, and theta naught is the angle of the projection, while v naught y is v naught sine theta naught. What we have in the horizontal motion, we can get from the horizontal motion the time of flight, as long as x may be given for the whole motion, this one, and v naught x, it's the same as vx. So we can get right away the time of flight. And this time can be used for the y motion. In the y motion, we can put the initial position here, the same as here, or x and y is 0. For the y motion, we have v naught y, that is v naught sine theta naught, multiplied by t minus half g t square. If v naught y is given as v naught and theta naught are given, in this case, you're going to use the t obtained from here and use it in this equation. And then you will be able to get y at the time you want it. I mean, if the projectile reaches a certain x here, for instance, here, at this point, then you're going to get the time at this point. Then the corresponding y is going to be this one, obviously, this one. So it means these two equations, you can give you y and x at any instant of time during the flight of the projectile. So in this case, we can get an equation for the path of the projectile by substituting t from the x motion, obtained from the x motion, into the y equation. And the equation here turns out to be this one. This is an equation of parabola, and this is an equation for the projectile motion of a symmetric trajectory. You see, it's very important here to know that, but this is a general formula for to get a theta naught, for instance. When you put theta naught equals 0, you have to see what's going to happen. And if you put theta equal 90, you should check and decide, as this is a simple conceptual question for students to answer.